Good evening, everyone. This is Arvind. I welcome you all to today's KEP session on the concepts of finite element analysis and computational fluid dynamics. As you all know, CFD and FE plays a major role in product design. They are useful to design product as well as to create the simulation that test a product in different environment and conditions. So now we have Harikrishnan who will share some concepts of FEA, followed by Sriram about the concepts of CFD. I hope you will have a very informative session and useful KEB session. So with no further delay, let's get started. Hari, it's all yours. Just take over.
Yeah, thank you, Arvind. So, yeah. Good evening, everyone. It is a pleasure to welcome you all. As it seems, I am going to be the one carry the meat first off of the session. You see, before getting into the new topic, everyone should know some basics about the concepts that they are getting introduced, like what we are going about to learn here. So, let me start with the basic question. What is FEA? So FEA is also known as finite element analysis. It is a simulation of any given physical phenomenon using a numerical technique called finite element method. So here, engineers use this computer-based technique by calculating how components are uh, likely to perform in real life application and reduce testing of physical prototypes to develop better products and also faster while saving on expenses. This advanced technique can determine how components may be impacted by exposure to extremes like various temperature and pressures, physical effects like mechanical stresses, and other aggressive chemical environments too. However, for a computer, it is just solving a bunch of equations where the physical properties or techniques have been described using partial differential equations. So yeah, along with this, several numerical techniques have been developed over the last few decades, and one of the prominent one today is finite element analysis. So I just give an introduction about what is FEA. So how it's going to work? We have to know how it works. FEA works. So yeah, and I also talked about real life parameters and equations earlier, right? So let me talk in depth about that. Here, user feeds all the necessary information to the software like material properties and accurate 3D model, geometries, assemblies, anything. However, it is important to know that FEA only gives an approximate solution to the problems and is is a numerical approach to get the real result using partial differential equations. For example, if a wind turbine rotates with a particular speed under certain conditions and want to predict the outcome, then FEA can be used. Here, FEA solves numerous equations and gives out a prediction of how the blades experience under the given conditions. So, so yeah, and the analysis works with a simple but powerful principle that is called the divide and conquer rule. Or also you can say that divide and conquer method. To make a precise simulation, the whole geometry is dissected up to millions of small elements that together forms the shape of structure. And in this, we call it as a mesh. So yeah, and mesh comprised of elements and nodes. As you can see in this right figure, the red mark is called element. There are more just for in a rectangular box there are totally 12 elements and there are numerous nodes you can see. So and also what you see, uh, so yeah, so here you see, one second. Yeah, So what you see here is mesh around a bicycle crank. Here the calculations are made for every single element, and combining all the individual results gives us this final result of the structure. This means we know values at certain points. We know values at certain points and within the elements, but not at every point. These certain points are called nodal points and are often located at the boundaries of the element. The accuracy of with which the variable changes is expressed by some approximations. For example, linear, quadratic, cubic equations, which are all you could have learned from mathematics. So, and yeah, let's say if this model is a 2D two dimension, then solving equation manually looks very simple and equations will be more likely linear. But this is a three-dimensional body. So the equations gets complex and practically impossible for one to solve by themselves. And here where we get smooth support from our user-friendly software called FEA, which takes care of all the complicated steps. And as you see here, the total number of as you see the statistics in the lower bottom, the total number of nodes present in after meshing is 6197, and the crank is in 3D model. And now, if you are try to calculate total number of equations to be solved, then that will be total number of elements into 3. So multiple of 3. And here it will be more than 18,000 equations to be solved. Too much, right? For someone to solve. But yeah, we have our software for helping us. So we talked about what is here. One of the important aspects we have to consider, and that is the density of the mesh, which can be altered based upon how complex or simple a simulation is needed. And a good finite element analyst starts with both an understanding of physics of the system that is to be analyzed and a complete description of the geometry of the system. In simple words, an analyst should know all the physics that are relevant to the problem, that is the material properties, the loads, the constraints, and any element that can affect the results of the interest. These inputs may have uncertainties in them. For instance, the material properties and the loads may not always be precisely known. It is important to keep this in mind during the modeling process, as there is no benefit in trying to resolve a model to greater accuracy than the input data admits. If you take a look at this, that the crank has holes in the both corners. If you take these corners, the mesh size differs compared to other spots. The surface inside the holes. So here it is a uniform meshing, but as you can see the surface outside, but it doesn't match, right? So here where the mesh refinement helps a lot. And as per this model, these three holes acts as a fixed support and greater force exerted on this spot. And this is the spot where we need more accurate information. This is where mesh refinement comes into greater play. So once all the information is assembled into a FEA model, the analyst can begin the preliminary. One second. Analyst can begin with the preliminary mesh. Early in this analysis process, it makes sense to start with a mesh that is as coarse as possible, like what is say in this image. This is a random model where the meshing is taken place, and first mesh is coarse mesh, and which has only 14 elements in it. So yeah, a coarser mesh is like a very large element. It looks something like this. So, and yeah, a coarse mesh will require less computational resources to solve, and yeah, it may give a very inaccurate solution. It can still be used as a rough verification and as a check on applied loads and constraints. And do you know why I said this can be used for verification? Because whatever the mesh size can be, which still the trend going to be alike. For instance, check this model itself. So yeah, check this model itself. Where so yeah. So yeah, again. So check this model itself where you can still examine the deformation of the model. So this is the deformation of the model where there is low deformation at one corner and high deformation at the other corner. But we can still be sure where the maximum deformation occurs in the crank. So here, but we don't know what is the accurate value of the maximum deformation. Here we have some value, but if you have a coarser mesh, then the value might be changed. Value might vary a lot. As final as possible, the deformation value, the maximum temp, the value, you can just measure it. So here where our next mesh refinement takes the role. Once all of this information is assembled into an FEA model, the analyst can begin this model refinement. Like they will be refining the mesh. So after computing the solution of on the coarser mesh, the process of the mesh refinement begins. So the mesh refinement is the process of resolving the model with successive finer and finer meshes, comparing the results between these different meshes. This comparison can be done by analyzing the fields at one or more points in the model, or by evaluating the integral of a field over some domains or boundaries. By comparing these scalar quantities, it is possible to judge the convergence of the solution with respect to the mesh refinement. Okay. As I mentioned earlier, accuracy is one of the main requirements to fulfill for the greater outcome. In real life, let's take a relationship between client and manager. Here, the client expects a product from the manager, and the manager should satisfy the client with a good service. So same goes for FEA. It should give you a good result. So now, what is the accuracy of your analysis? To give an answer for this, first we have to analyze the necessity of to fully understand the application where the component is going to be used, and more often where the component is going to be used, how the other conditions, how like the environment check, if the component is going to be used in some harsh environment like in oil industry or somewhere in marine, then you have to consider those environment possibilities. And then more often the inaccuracy arises due to data is extrapolated. This is something important because interpolation is acceptable, but extrapolation leads to misfortune. So to get an accurate result or permissible limits, one should know exact application of the component, typical loading conditions, and of course, what material is going to be used for the construction. And yeah, utilizing FEA, an approximation can be made for the points using different modes of accuracy. There is a a square approximation, a polymer approximation, and a discrete approximation. Each of these techniques increases in accuracy and complexity also. One of the best thing about FEA is we don't have to complicate ourselves with these methods and leave it to the hands of our software. So also, I like to mention when complexity of the problem increases, accuracy also increases. So yeah. So we had a long talk about FEA itself. Now let's see where it can be used. The application of finite element method or just starting to reach their potential. One of the most exciting prospects is its application to coupled problems like fluid structure, interaction, thermomechanical, thermochemical, electromagnetics, and other relevant areas. However, a powerful tool like FEA is now used to solve design problems in mechanical and other engineering fields like aerospace and defense, automotives, and electromechanical and consumer goods, heavy engineering, lot more. And in practice, engineers use finite element modeling software on a huge variety of tasks. Some critical analysis where FEA definitely going to be used, or vibration and impact task, buckling, contacts to know how the objects are colliding, and fatigue, heat transfer, and thermal deflection, and stresses a lot more, creep and relaxation too. To make it clear, FEA is not provided an individual software. Like it won't be available as a whole, as an individual product in the market, and rather comes as one of the package in variety of softwares. Some notable software packages that implement the finite element methods are ANSYS, Autodesk, Nastran, and COMSOL. So yeah, why the software packages became an essential part for an engineers. So far, FEA simulation enables design engineers to highlight potential area of weaknesses in the component, impact the overall application's efficiency or its ability to function in a given application. The range of benefits associated with FEA simulation make the technique highly favorable when it comes to developing solution or particular demand or complex application. The nature of FEA offers more advantages. It helps neglecting the need for real-life testing and allows the modeling of multiple material types and testing of complex geometry, which helps in improving the versatility of the component. It also provides an analysis accurate enough to isolate the exact area or location where performance is weak or require modification and improving time efficiency. Moreover, FE helps us to gain a more thorough understanding of the general behavior of the product and the nature of the application as a whole too. We can demonstrate few common real-life examples like study of car deformation and on impact, stresses on human joints, and creep deformation over turbines. As just we have a very few varied applications. Finite element analysis is only a predictive model, as it doesn't confirm that a design will survive the modeling stresses, but it gives engineers a clearer picture of how the design will react to stresses and reduce the need for extensive prototypes. As same goes for this bicycle crank. We just know how when the force is applied to a surface, we get to know how the component is going to be performed. So we don't know how many cycles it may like we can't give an exact solution, like say these many cycles it can provide us, and it will be giving a breakdown after these many cycles. So yeah, it so for an extent, FEA is the best software for us to understand how the component works in the first place. So yeah, and now whatever software we use, running a FEA analysis is going to be quite similar. These are few steps that can be followed in every software. So yeah, in order to incorporate FEA into your design, you need to have a particular goal, like what are you wanting to achieve, like improving strength or reduce the mass or etc. If your goal aren't clear, then FEA process is pointless. And it is clear that one has to create a solid model of the object. In other words, feeding the software with model geometry and the material properties as appropriate. Later, the geometry should be cross-checked. And yeah, cross verification in each step is required to not get out of track anywhere else. And yeah, and already I told you about the meshing the model. As and next step is applying loads and constraints to the model. In short, inputs from user with a good understanding of how the system is interacting with its surroundings. And finally, run the model. So yeah, sorry. And run the model with numerous quality checks that required from the model, like error plots, reaction force, stress results, etc. So in case of our crank, given inputs or directional forces. So yeah, you can see here, like this is given inputs or directional forces and a fixed support. So inputs. So yeah, the direction of the force given is towards the positive y-axis. So yeah, wait, positive y-axis, and the fixed support is something is provided over this three holes, these three surfaces. These three surfaces will be fixed at one point and it will be having a zero force. So yeah, the quality checks carried out total deformation and yeah, total deformation, normal stresses along different directions, and the force reaction, which are some quality checks, and made sure the model gives precise results for respective user inputs. So as I said earlier, the force is given towards the positive y-axis, and now and this three holes, this spot will be like stationary and it won't be having any movement. This is the so when you go for a total deformation, you get to know that these blue marks are like zero minimum, and that definitely proves you that this is completely stationary, and this is the having the maximum deformation, and it occurs in the other corner of the bicycle crank. So this helps us to understand that the inputs what we given is validated with the output. So our model, we given a model that is precise enough. So this is how FEA works. And then finally a report should be made with all the data obtained from the software and analyzed. So whatever the force, we have given a certain force value over here, and there will be a for this force the deformation value is around this much. So you're just calculating, you are just predicting how much there will be a net deformation. That can be helpful for you to build a model in real life too, and in their own conditions. So yeah, in the end, let's get to the end. Now, FEA is a crucial step that you can easily add to your development program. It will save your significant time and money by highlighting problems and finding solutions during your product design phase itself, before any material is ordered or before you even contemplate the cutting stage. FEA is just one of the digital technologies transforming the future of engineering. Yeah, and you will be having a more, you can get a more accurate answer value also. It depends, but it depends on your simulation procedure, what you follow. So now, thank you all, and now I like to ask Sriram to take over. He will be speaking about CFD, which will be more interesting than mine. Thank you.
Hey guys, I'm Sriram and I want to talk about computational fluid dynamics applications in safety. So let's start with what's safety. So computational fluid dynamics here refers to the analysis of fluid flows using numerical solution methods. So numerical solution methods here, it means a set of differential equations or governing equations also that help us analyze the fluid flow and predict the unknown values. So governing equations here itself are a set of equations like conservation of mass, conservation of momentum, heat and mass transfer equations. Those partially, so those differential equations, which help us to predict the unknown values or compute the unknown values just by knowing the few known values. So there are three steps in safety: pre-processing, simulation, and post-processing. So in pre-processing, as Harikrishnan mentioned, it is the creation of geometry and meshing also. So in meshing, what we do is we assign nodes, we create meshes in order to assign nodes in certain locations of the geometry. So since ANSYS is a finite element software, so it will just calculate or use a governing equation to calculate the values at those nodes. Again, so meshing depending, so choosing the right mesh also is an important factor, since choosing fully fine mesh will result in an unstable mesh, and you might end up wasting a lot of time and resources. And simulation part. So in simulation, for this session, we're using uh, ANSYS Fluent, which is mainly used for CFD and fluid flow um, processes. And for post processing, is basically you create the graphs and contours, and based on the final results, we analyze it quantitatively and qualitatively. So in order to understand uh, or gain insightful results, so we just have to understand the concept first. So let's hope, since we are working on an airplane, airfoil, so let's understand what are the forces acting on an airplane. So an airplane consists of lift, drag, thrust, and weight. So the main purpose of airfoils is to provide enough lift to counter the weight of the plane. That is, you need to increase lift and reduce drag in order to obtain the optimum condition that will counter the weight of the airplane and the airplane can fly. So let's understand how the airfoil achieves or provides the situation. The airfoil, when the air strikes the airfoil, the top region of the airfoil travels a longer distance. So when it travels a longer distance, it generates a low pressure region. And the low pressure, due to the low pressure region, uh, you will also get high velocity speeds. And again, when the air passes through the bottom region of the airfoil, it travels at high pressure and at low velocity. So what happens is, since the bottom part of the airfoil has high pressure and the top foil has low pressure, there's a shift lift. So as we know, the pressure shifts from the region of high pressure to a region of low pressure. So due to the pressure difference, lift is generated. So the main purpose of airfoil is to create this situation. So the main forces that we'll be focusing on this simulation are lift and drag. So we need to minimize drag and maximize the lift force. So boundary layer. So when it comes to meshing, we'll be giving the utmost importance to the boundary layers. We'll be performing certain operations like face sizing, body sizing, and inflation while meshing, because the boundary layer is a part of the airflow code closest to the surface of the aircraft. It is where the lift, drag, and other operations or other forces that take place. So we need to focus on the boundary layer in order to obtain the perfect values and minimize drag and maximize lift. Again, our objective is to obtain an airfoil that produces high lift and low drag. Aerodynamics of an F1 car. So, so in order to understand how an F1 car works, let's just consider an F1 car an upside down version of an airplane. Okay, I mean airplane or the wing. So what happens is, as we discussed in the previous slides, the airfoil or the airplane wings, they are designed in such a way that the lift is maximum and the drag is minimum. That is, the airfoil generates a circumstance, a situation where uh, the region below the airfoil is a region of high pressure and region above the airfoil is a region of low pressure. So, which in order generates lift. So what happens here is it's an upside down motion of an airplane. So as we know that an F1 car travels at a speed of around 320 kilometers per hour. That's the top speed. So when a car travels at such insane speeds, so the amount of forces that the car generates and is like way too much. That is, it can easily generate force that is more than 2 times the weight of the car. So what happens when you generate so much force? Uh, it may result in car flipping over because of uh, because of such high forces. So what do we do in order to keep the car on the track is we install these rear wings and the front wings. So what happens is these rear and front wings or the bodywork in general generate downforce. So downforce is basically opposite of lift. So as we know, the lift pushes the pushes the airplane from the ground, while the downforce ensures that the car stays on the ground. As air passes over the bodywork, it forces the car into the track. So what happens is if a car has more downforce, then the car can easily take sharp corners or typical corners easily at a high speeds. Downforce usually comes at the cost of drag. So if you want more top speed, you have to reduce the downforce, but not you shouldn't reduce the downforce too much that the car just slips. So the F1 car teams, they usually make proper adjustments or balances in order to obtain the optimum conditions for perfect corner, or it depends on the circuit where they are racing. So let's assume what happens if the car has less downforce. So this is an animation how it works. Uh, so this is a video that happened on 2012 Chinese Grand Prix, which shows what happens if a car has less downforce. So as you can see, the car was about to just take off. I mean, uh, the car was about to take off, which implies that the car has less downforce, and he already lost a couple of seconds. So we should understand how the important downforce plays a role in F1 car in order to travel at high speeds. So let's start with the analysis part. So what you see on the screen, it's called ANSYS Workbench. So this is the place where we'll be working on a project or simulation. So on the left side of the workbench screen, you can notice an option called Toolbox. So Toolbox is where you can find different types of packages or packages of simulations that you can perform. So these packages are available under the analysis system toolbox, and there are other standalone systems, let's say. So those are called as component systems. So when you see the component systems here, there's one separate standalone system for geometry, for mechanical model mesh, and polyflow, etc. So so the purpose of using component systems is for a better understanding, and it's more like a flowchart kind of thing where you can uh, it'll be more systematic way to approach. But for beginner's purpose, for a beginner, it's better we start with an analysis system toolbox where where you get package or everything clubbed in to a single toolbox, like here. So in this, it has all the steps that are needed in order to complete a simulation and obtain the required results. Whereas in standalone systems, even I'll achieve the same thing, but I have 4 different standalone systems. The main reason I have created is in order to explain the different types of different steps involved in CFD, that is pre-processing, simulation part, and the post-processing part. So as we have discussed in the previous slides, pre-processing involves creating a geometry and the mesh. So let's let's get started. Okay. I guess it's getting see the screen now. So here you can notice the egg foil. This is the main model that comes in the geometry part. So geometry, as we have discussed before, you can import the geometry using the space game or create a geometry, custom geometry using design modeler. I would prefer the former because there are there are friendly softwares like SolidWorks, Fusion 360, etc. And and it's very easy to import using space game. But design modeler is also it's useful. I mean, uh, it isn't that tough, but not user friendly though. So here under the geometry, you can see what I go for. So here is the surface body, uh, and automatically it has classified it. It has breakdown into. So under the materials, we can assign what material material you want. But since it's a beginner level um, simulation, we don't have to focus much on this. And coordinates also it's useful when you are using complex geometries or when you wanna choose a different frame of reference. Uh, so yeah, another thing is meshing. Meshing is an important part because in as a student version, we have a limitation of the number of nodes that we can use. So it is important that we choose we use more nodes on areas uh, where we want to and not just entirely like use more nodes on the entire geometry. So here what we have done is one second. So here under the mesh we have done sizing, edge sizing, face sizing, and body sizing. So body sizing it involves um, so basically sizing means increasing the number of nodes in layman terms. So what we have done is we have uh, we have increased the number of nodes on the space, that is space sizing, and body sizing we have just increased the first the mesh was a bit rough. I mean, not proper uniform mesh. It was a bit rough. So we have used body sizing for that to increase the nodes to some extent. And there's something called inflation. So can you notice a few layers here compared to the rest of the mesh? You can notice there are few uniform layers along the boundary layer. So that is called inflation. So inflation is basically adding a set of layers. So uh, the reason why we are doing this because in airfoil along the boundary layer itself, all the lift, drag, everything happens. So we want to get as accurate results as possible without getting much errors. So we need more number of nodes in order to get uniform and accurate results that are reliable. So once this meshing is done, so another important part of pre-processing is naming your selections. So can you notice here I have named few selections called inlet, outlet, the airfoil, and the symmetrical walls. So symmetrical walls is not needed, but it's better if you use the inlet out if you need inlet outlet and the airfoil. It's because when you work on the fluent, it's easier to choose which phase you want to consider for boundary for you want to consider or give the boundary equations. And yeah, so that's it about the pre-processing part. So if you want to use the name selections, you want to name a site, In ANSYS, in geometry, in design modeler, you can use right click and you can just right click on the piece. Oh, yeah, here itself you can show. There's an option for create name selection. So once you create click on this option, you can just type in name for sim or simply, and that's apply selected geometry. Click on OK. So that's it about the meshing and the pre-processing part. So now we'll work on the simulation part. So this will be carried on ANSYS Fluent. And now what you see is actually workspace. So under Fluent workspace, we have to choose what type of model we are going to work on, simulation model we are going to work on. And since we're working on aerodynamics of an airfoil, so which involves uh, fluid flow, I mean air fluid. So we'll be using the viscous SSTK omega model. And yeah, uh, to under this K viscous model, you have to choose K omega because usually another option we choose that. I guess it's K epsilon. So K epsilon or transition SST. But you have to choose the K omega equation. And under the K omega model, you have to choose SST. And the model constraints are given by default. You don't have to alter it much. Click on OK. So once the simulation model is generated, what type so you just check the materials. So what type of fluid the airfoil is gonna get in contact with? Air. I mean, yeah, it's air, and the solid, the airfoil material is aluminum. Since typically in airplanes, something similar to aluminum since so we are using aluminum, and cell zone conditions is not needed. It's automatically set by default. But boundary conditions here where you focus on uh, what inputs you have to give. So remember while meshing, we have no we have created something called the name selections. The reason why we have created name selections is uh, this software identifies that and it automatically gives of the boundary conditions. Uh, so under inlet, we have to give the inlet velocity, the velocity at which the air strikes the airflow. For we have created like considered a sample case in which the velocity of the air that strikes the airfoil is 12 meters. Okay. So once it strikes, um, so these are few random zones that the software has created, so you don't have to alter much. An outlet, note that the outlet should be in pressure. You don't want the velocity. So make sure the inlet should be in inlet. You are giving the velocity input, and the output that you need pressure output. So yeah, focus on that, and you don't have to monitor much. So when it comes to solutions, yes, yeah, when it comes to solution, you have to make sure we are using second order discretization, and everything is in second order. There are few controls which you don't have to worry about unless you know any of the any of the parameters that you want to change. For basic simulations, you don't have to alter them. Fit with these values. And initialization. So initialization, it involves, there are two initializations, hybrid and standard. So in hybrid, actually what happens is, the based on the boundary conditions, the software itself had choose the appropriate initializing methods. While in standard, it's more like you have to specify what are the exact boundary conditions you need. So for a beginner's level, it's better you use the hybrid initialization method, so that the software does the work for you. And here, when it comes to compilation, you can choose number of iterations. I have given 1200 iterations so that I get reliable values. So okay, then this results we can check on post CFD post. So once you enter the number of iterations you need and the reporting interval, here it's given 1 second. So you just click on the calculate button and the console will do the work for you. You will be running 1200 iterations and you'll be getting a plot like this. Uh, at starting, you can see fluctuations, but once the iterations keep on increasing, you can notice that we are getting a reliable values. And same goes for lift. At starting, we had some fluctuations, but as the iterations kept on increasing, so we got a reliable value that isn't fluctuating much. So yeah, for creating contours, you can create it from here also, but it's better in EMP post also you can do. But yeah, and for the plots that you need, report definitions. Yeah, it's important that in order to obtain these graphs, you need reports. So for creating a report, you can just click on the report definitions and create a new one, post report. You will be getting few options here, drag left and so click on drag and choose what type of coefficient you need. Choose wall zone, that is airfoil. Yeah, we want to find the drag on the airfoil, and here force vector is the direction at which the hits the air hits the airfoil. So basically, the in this condition, it's along the x direction already. Horizontally. So if you want to change the direction, you can change the coordinates as per the requirements, and then you just click on create output parameter and click on OK. That's it, and that's it about the Fluent workspace. So there are uh, two types of iterations: first order iteration and second order iteration. So in first order iteration, um, we choose a second order iteration. I have explained, like I have checked. I guess I have explained in the previous slides on previous. I have explained it before. I guess yeah, here during the boundary cell zone conditions, I guess. Uh, the reason why we choose second order is The second order iterations are more accurate but less stable compared to the first order iterations. So what we need here is more accuracy. I have chosen accuracy, so that's why I have chosen the second order iterations. And that's it about the answer simulation part. So now we'll go on to post processing. So post processing involves presenting graphs and other visualizations that we need in order to provide valuable insights. So here I have created contours and few graphs. So in order to create a velocity contour like this, so what you do is there's an option here, contour, insert name. Let's give pressure to. So location, airfoil, variable, pressure, range. You just set it as global and loop. So number of contours you can give as much as you want, but it's better. Yeah, it's better if you give more contours because you will get various frames. And just click on apply. So so as you see, you can barely notice any contours here. So in order to, but here on the pressure, let's give around 100 contours. Apply. Yeah, you can notice. So that's about the contours here, and for velocity we have a velocity contour, uh, which explains how the air flow, how the turbulence is generated. So here you can see the velocity is more on the upper side compared to the lower, and the few vortexes or turbulence that is generated here. Okay, so this is the velocity stream. That is the airflow. So as the air travels faster in the above region, the low pressure region is created, and the below is comparatively high pressure. Uh, Even you can notice in the pressure contour, the above one has lower pressure compared to the below. So the pressure goes on from the region of high pressure to a region of low pressure, and that's when lift is generated. On so you can also add velocity streams, streamlines, vectors, and you can also animate. That's it about the CFD post processing part.
Thank you, Harikrishnan and Sriram, for your wonderful and informative session. I also thank each and everyone who attended the KEP session today. I hope you have enjoyed it and learned something new from the session today. And thank you. As you know, it is not the overall concept of FEA and CFD. It's just a fraction of the complete thing. But you always have the opportunity to learn more. And before saying the final goodbye, if any of you have any doubts or queries, you can just leave them in the chat box, and we'll be trying to answer them in the chat box itself. Thank you. Thank you all.